All right, so in problem 27, it says when two births are randomly selected, the sample space for genders is two boys, a boy and a girl and a boy, and then two girls. So those are the four possibilities. Assume that those four outcomes are equally likely. Construct a table that describes the sampling distribution of the sample proportion of girls from two births. Okay, so what we want to build is a small table where we look at each combo. So they had boy, 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 girl, girl, boy, girl, girl. And then they want to look at the proportion of girls. Okay. Well, the proportion of girls is just how many girls were there in this combination. So in boy-boy combination, there are 0 girls out of 2 babies. In boy-girl combination, there's 1 girl out of 2 babies. In girl-boy combination, there's 1 girl out of 2 babies. And then for girl-girl, there are 2 girls out of 2 babies. So those are the proportions. And if we turn these into decimals, this would be 0. This would be 0.5, this would be 0.5, and this would be 1. So the sample proportion of girls is, these are our possible answers. They want us to enter as lowest, smallest to biggest, so it would be 0, 0.5, and then 1. Now what's the probability of this? Well, the probability is just count how many we have. So we had 1 0, we had 2 0.5s, and we had 1 1. And to make them a probability, it would be out of 4 combinations. So there were 4 combinations here. One of them was a 0, 2 of them were halves, 1 of them was a 1. Okay, so that'd be the answer to the first part. And then just like before, so in all problems in this section, what we did next was take each of these numbers times their probability. So the mean proportion of girls would equal, and I'm going to do the shortcut method I showed towards the end of class, just take each of these numbers here times the first number. So it'd be 0 times 1 plus 0.5 times 2 plus 1 times 1 all over 4. So just take each of these numbers times the numerator of these fractions and then divide them all by 4, since they all have a common 4 in the denominator. This would be 0, this would be 1 plus 1, this is 2 over 4, this is 1/2. So the mean of the sample proportions is 1/2. Now we need to compare that to the mean of the actual population. So for the population proportion, you would have, there's several ways to do it, but if you look at these combinations, these 4 different combos, there are 1, 2, 3, 4 girls out of 8 births. So the proportion of girls in the population was, there were 4 girls out of 8 births, which is 1/2. And we see again that these are the same. And so now we can answer, do the mean of the sample proportions equal the proportion of girls in 2 births? Okay, so I didn't quite do this. Girls in 2 births, it would still be 1/2 though. So either way, you can get to this 1/2. So yes, both the mean of the sample proportions and the population proportions are 1/2. So B. D, or excuse me, the next part, does the result suggest that a sample proportion is an unbiased estimator of population proportion? So anytime these are equal, then that means yes, they're unbiased estimators. So yes, because the sample proportions and the population proportions are the same, A. Okay. Last table problem. We have another kind of gender one. So a genetics experiment involves a population of fruit flies containing one male named Carl and 3 females named Diane, Emily, and Fiona. Assume that 2 fruit flies are randomly selected with replacement. So we have 4 things here with replacement, so we're going to have another table we have to build. And this is going to ask about the proportion of males. The proportion of males. So let's make a note that Carl here is the only male. So I'm going to assign the letter M to him. And then for the female fruit flies, I'm going to leave their first letter of their names as the to build the table. So what we have is we have a table where we say we have Carl the male, then we have Diane, Emily, and Fiona. And then we're going to repeat these 4 letters going down. So it would be M, D, E, and F. And then we're going to repeat these 4 letters going across. So it would be M, D, E, and F. M, D, E, and F. Just repeat these 4 letters all the way across in each column. Okay. Then we're going to repeat these 4 top letters going down. So it's going to be comma M, comma D, comma E, comma F, comma M, comma D, E, F. So I'm just repeating these 4 in each row. Comma M, comma D, comma E, comma F, M, D, E, F. And there's the table. So that table shows all 16 different combinations of fruit flies that you could get if you randomly select 2 of them. Actually, you randomly select 1 of them with replacement. So you pull one out, record which one you got, put it back, let them fly around for a bit, pull out another one, record which one you got, put them back. And these are the 16 possibilities you could have. Okay, so now they want the proportion of males. So in this first one, I grabbed Carl twice. So that means I had 2 males out of 2 tries. In this one, I had Carl and then Diane, so that's 1 male out of 2 tries. Then ME would be 1 male out of 2. MF would be 1 male out of 2. Down here, second row, Diane and Carl would be another 1 male out of 2. Diane twice would be 0 males out of 2. Diane and Emily would be 0 males out of 2. DF is 0 out of 2. So I'm just looking for M, really. Here's 1 M out of 2 letters. 0 M's out of 2 letters. 0 out of 2, 0 out of 2. Running out of room down here. Let me write these down here. 1 out of 2, 0 out of 2, 0 out of 2, and 0 out of 2. So let's count the zeros. So anything with a 0 is going to be, the proportion is 0. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9. So we had 9 zeros out of 16 combos. Let's count the halves. So the halves would be 1, 2, 3, 4, 5, 6. 6 out of 16. And that's 15 out of 16, so there should only be one left. 1 would be 2 out of 2. It's right here. It should be only one of those. And that's correct. So 1 out of 16. Okay, now they want us to find the mean of the sampling distribution. So this is actually pretty simple. The mean of the sample would be, there is 1 male out of 4 flies, so it would be 0.25. The harder part, as it always is getting the mean of the sampling proportions, which would be each of these numbers times their fractions. So let's do that right down here. The mean of the sampling proportions would be 0 times 9 plus 0.5 times 6 plus 1 times 1, all divided by 16. 0 is going to kill this 9. Half of 6 is 3 plus 1. This would be 4 over 16. This is 0.25. And once again, just like the last problem, we see that these two numbers target each other. They're equal. So is the mean of the sampling distribution from part B equal to the proportion? Yes. If so, does the mean of the sampling distribution always equal the population proportion? We should get yes here, double yeses. So the answer is D. Yes, the sample mean is equal to the population proportion of males. These values are always equal because proportion is an unbiased estimator. Okay, so that completes the computation ones, and now we've seen this many times. So hopefully we have it locked in now. The last two should just be some vocab review. So we have 29. Blank is the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. This is called the sampling distribution of a statistic. And it's basically something like this, where you draw all possible combinations. Okay, the last one for this section. 30. Which of the following is not a property of the sampling distribution of the variance? So the mean of the sample variance is the population variance, so that was true. The expected value of the sample variance is equal to the population variance, that was also true. That's just another way of saying this. The sample variances target the value, yes, that's also true. So the only one that's not true is A. The distribution of sample variances tend to be a normal distribution. That is not true, they tend to be skewed. And that will do it for 6.3.